The Monty Hall problem is a brain teaser, in the form of a probability puzzle, loosely based on the American television game show Let's Make a Deal and named after its original host, Monty Hall. The problem was originally posed in a letter by Steve Selvin to the American Statistician in 1975. It became famous as a question from a reader's letter quoted in Marilyn vs. Savant's Ask Marilyn column in Parade magazine in 1990. Suppose you're on a game show, and you're given the choice of 3 doors. Behind one door is a car. Behind the others, goats. You pick a door, say no A1, and the host, who knows what's behind the doors, opens another door, say no A3, which has a goat. He then says to you, do you want to pick door no A2? Is it to your advantage to switch your choice? Vos Savant's response was that the contestant should switch to the other door. Under the standard assumptions, contestants who switch have a 2/3 chance of winning the car, while contestants who stick to their choice have only a 1/3 chance. Many readers of Vos Savant's column refused to believe switching is beneficial despite her explanation. After the problem appeared in Parade, approximately 10,000 readers, including nearly 1,000 with PhDs, wrote to the magazine, most of them claiming Vos Savant was wrong. Even when given explanations, simulations, and formal mathematical proofs, many people still do not accept that switching is the best strategy. Paul Erdős, one of the most prolific mathematicians in history, remained unconvinced until he was shown a computer simulation confirming the predicted result. The problem is a paradox of the veridical type, because the correct result is so counterintuitive it can seem absurd, but is nevertheless demonstrably true. The Monty Hall problem is mathematically closely related to the earlier 3 prisoners problem and to the much older Bertrand's box paradox. The paradox, Steve Selvin wrote a letter to the American Statistician in 1975 describing a problem loosely based on the game show Let's Make a Deal, dubbing it the Monty Hall problem in a subsequent letter. The problem is mathematically equivalent to the 3 prisoners problem described in Martin Gardner's Mathematical Games column in Scientific American in 1959 and the 3 shells problem described in Gardner's book Aha Gotcha. The same problem was famously restated in a 1990 letter by Craig Whittaker to Marilyn vs. Savant's Ask Marilyn column in Parade. Suppose you're on a game show, and you're given the choice of 3 doors, behind one door is a car. Behind the others, goats. You pick a door, say no A1, and the host, who knows what's behind the doors, opens another door, say no A3, which has a goat. He then says to you, do you want to pick door no A2? Is it to your advantage to switch your choice? Standard assumptions, the behavior of the host is key to the 2/3 solution. Ambiguities in the Parade version do not explicitly define the protocol of the host. However, Marilyn vs. Savant's solution printed alongside Whittaker's question implies, and both Selvin and vs. Savant explicitly define the role of the host as follows: the host must always open a door that was not picked by the contestant, the host must always open a door to reveal a goat and never the car, the host must always offer the chance to switch between the originally chosen door and the remaining closed door. When any of these assumptions is varied, it can change the probability of winning by switching as detailed in the section below. It is also typically presumed that the car is initially hidden behind a random door, and that if the player initially picked the car, then the host's choice of goat hiding door to open is completely random. Some authors, independently or inclusively, assume the player's initial choice is completely random as well. Selvin, vs. Savant and the media furor. Vos Savant wrote in her first column on the Monty Hall problem that the player should switch. She received thousands of letters from her readers, the vast majority of which, including many from readers with PhDs, disagreed with her answer. During 1990–1991, 3 more of her columns in Parade were devoted to the paradox, and the discussion was replayed in other venues, and reported in major newspapers such as the New York Times. In an attempt to clarify her answer, she proposed a shell game to illustrate: you look away, and I put a pea under one of 3 shells. Then I ask you to put your finger on a shell. The odds that your choice contains a pea are 1/3, agreed? Then I simply lift up an empty shell from the remaining other 2. As I can do this regardless of what you've chosen, We've learnt nothing to allow us to revise the odds on the shell under your finger. She also proposed a similar simulation with 3 playing cards. Despite further elaboration, many readers continued to disagree with her, but some changed their minds and agreed. Nearly 100% of those who carried out Savant's shell simulation changed their minds. About 56% of the general public and 71% of academics accepted the answer. Savant commented that though some confusion was caused by some readers not realizing that they were supposed to assume that the host must always reveal a goat, almost all of her numerous correspondents had correctly understood the problem assumptions, and was still initially convinced that Savant's answer was wrong. Solutions: simple solutions. The solution presented by Savant in Parade showed the 3 possible arrangements of 1 car and 2 goats behind 3 doors and the result of staying or switching after initially picking door 1 in each case. A player who stays with the initial choice wins in only 1 out of 3 of these equally likely possibilities, while a player who switches wins in 2 out of 3. An intuitive explanation is that if the contestant picks a goat, the contestant will win the car by switching, as the other goat can no longer be picked, while if the contestant picks the car, the contestant will not win the car by switching. The fact that the host subsequently reveals a goat in one of the unchosen doors changes nothing about the initial probability. Another way to understand the solution is to consider the 2 original unchosen doors together. As Cecil Adams puts it, Monty is saying in effect, you can keep your 1 door or you can have the other 2 doors. The 2/3 chance of finding the car has not been changed by the opening of one of these doors because Monty, knowing the location of the car, is certain to reveal a goat. So the player's choice after the host opens a door is no different than if the host offered the player the switch from their original chosen door to both remaining doors. The switch in this case clearly gives the player a 2/3 probability of choosing the car. As Keith Devlin says, by opening his door, Monty is saying to the contestant there are 2 doors you did not choose, and the probability that the prize is behind one of them is 2/3. I'll help you by using my knowledge of where the prize is to open one of those 2 doors to show you that it does not hide the prize. You can now take advantage of this additional information. Your choice of door A has a chance of 1 in 3 of being the winner. I have not changed that. But by eliminating door C, I have shown you that the probability that door B hides the prize is 2 in 3. Savant suggests that the solution will be more intuitive with 1 million doors rather than 3. In this case there are 999,999 doors with goats behind them and 1 door with a prize. After the player picks a door, the host opens all but one of the remaining doors. On average, in 999,999 out of 1 million times that remaining door will contain the prize. Intuitively, the player should ask how likely is it, that given a million doors, he or she managed to pick the right one initially. Steibel al. Proposed working memory demand is taxed during the Monty Hall problem, and that this forces people to collapse their choices into 2 equally probable options. They report that when increasing the number of options to over 7 choices, people tend to switch more often. However, most still incorrectly judge the probability of success at 50/50. Solutions using conditional probability. The simple solutions above show that a player with a strategy of switching wins the car with overall probability 2/3, that is, without taking account of which door was opened by the host. In contrast, most sources in the field of probability calculate the conditional probabilities that the car is behind door 1 and door 2 are 1/3 and 2/3 given the contestant initially picks door 1 and the host opens door 3, Morgan al. 1991, Chun 1991. Gilman 1992, Carlton 2005, Grinstead and Snell 2006 137 €138, Lucas al. 2009. The solutions in this section consider just those cases in which the player picked door 1 and the host opened door 3. Refining the simple solution, if we assume the host opens a door at random, when given a choice, then which door the host opens gives us no information at all as to whether or not the car is behind door 1. In the simple solutions, we already observed that the probability that the car is behind door 1, the door initially chosen by the player, is initially 1/3. Moreover, the host is certainly going to open a door, so opening a door does not change this. 1/3 must be the average probability that the car is behind door 1 given the host picked door 2 and given the host picked door 3 because these are the only two possibilities. But these two probabilities are the same. Therefore they are both equal to 1/3. This shows that the chance that the car is behind door 1 given that the player initially chose this door and given that the host opened door 3 is 1/3, and it follows that the chance that the car is behind door 2 given the player initially chose door 1 and the host opened door 3 is 2/3. The analysis also shows that the overall success rate of 2/3, achieved by always switching, cannot be improved, and underlines what already may well have been intuitively obvious. The choice facing the player is that between the door initially chosen, and the other door left closed by the host, the specific numbers on these doors are irrelevant. Conditional probability by direct calculation. By definition, the conditional probability of winning by switching given the contestant initially picks door 1 and the host opens door 3 is the probability the car is behind door 2 and the host opens door 3 divided by the probability the host opens door 3. These probabilities can be determined referring to the conditional probability table below, or to an equivalent decision tree as shown to the right. The conditional probability of winning by switching is 3 plus 1/6, which is 2/3. The conditional probability table below shows how 300 cases, in all of which the player initially chooses door 1, would be split up, on average, according to the location of the car and the choice of door to open by the host. Bayes' theorem. Many probability textbooks and articles in the field of probability theory derive the conditional probability solution through a formal application of Bayes' theorem. Among them Gill, 2002 and Hens, 1997. Use of the odds form of Bayes' theorem, often called Bayes' rule, makes such a derivation more transparent. Initially, the car is equally likely behind any of the three doors, the odds on door 1, door 2, and door 3 are 1-1-1. This remains the case after the player has chosen door 1, by independence. According to Bayes' rule, the posterior odds on the location of the car, given the host opens door 3, are equal to the prior odds multiplied by the Bayes factor or likelihood, which is by definition the probability of the new piece of information under each of the hypotheses considered. Now, since the player initially chose door 1, the chance the host opens door 3 is 50% if the car is behind door 1, 100% if the car is behind door 2, 0% if the car is behind door 3. Thus the Bayes factor consists of the ratios 1/2 or 1 or 0 or equivalently 1 or 2 or 0, while the prior odds were 1 or 1 or 1. Thus the posterior odds become equal to the Bayes factor 1 or 2 or 0. Given the host opened door 3, the probability the car is behind door 3 is 0, and it is twice as likely to be behind door 2 than door 1. Richard Gill, 2011 analyzes the likelihood for the host to open door 3 as follows. Given the car is not behind door 1, it is equally likely that it is behind door 2 or 3. Therefore, the chance that the host opens door 3 is 50%. Given the car is behind door 1, the chance that the host opens door 3 is also 50%, because when the host has a choice either choice is equally likely. Therefore, whether or not the car is behind door 1, the chance the host opens door 3 is 50%. The information host opens door 3 contributes a Bayes factor or likelihood ratio of 1 or 1, on whether or not the car is behind door 1. Initially, the odds against door 1 hiding the car were 2 or 1. Therefore the posterior odds against door 1 hiding the car remain the same as the prior odds, 2 or 1. In words, the information which door is opened by the host reveals no information at all about whether or not the car is behind door 1, and this is precisely what is alleged to be intuitively obvious by supporters of simple solutions, or using the idioms of mathematical proofs, obviously true, by symmetry. Direct calculation, consider the events C1, C2 and C3 indicating the car is behind respectively door 1, 2 or 3. All these three events have probability 1/3. The player picking door 1 is described by the event x1. As the first choice of the player is independent of the position of the car, also the conditional probabilities are p, psi x1, equals p1, psi, equals 1/3. For ease of notation, the conditional probability given x1 is denoted by p1. The host opening door 3 is described by h3. For this event it holds. Then, if the player initially selects door 1, and the host opens door 3, the conditional probability of winning by switching is. Strategic dominant solution. Going back to Nalaboff, the Monty Hall problem is also much studied in the literature on game theory and decision theory, and also some popular solutions correspond to this point of view. Savant asks for a decision, not a chance. And the chance aspects of how the car is hidden and how an unchosen door is opened are unknown. From this point of view, one has to remember that the player has two opportunities to make choices: first of all, which door to choose initially, and secondly, whether or not to switch. Since he does not know how the car is hidden nor how the host makes choices, he may be able to make use of his first choice opportunity, as it were, to neutralize the actions of the team running the quiz show, including the host. Following Gill, 2011, a strategy of contestant involves two actions: the initial choice of a door and the decision to switch, which may depend on both the door initially chosen and the door to which the host offers switching. For instance, one contestant's strategy is choose door 1, then switch to door 2 when offered, and do not switch to door 3 when offered. 12 such deterministic strategies of the contestant exist. Elementary comparison of contestants' strategies shows that for every strategy A there is another strategy B. Pick a door, then switch no matter what happens, which dominates it. No matter how the car is hidden and no matter which rule the host uses when he has a choice between two goats, if A wins the car then B also does. For example, strategy A, pick door 1 then always stick with it, is dominated by the strategy B, pick door 2 then always switch after the host reveals a door. A wins when door 1 conceals the car, while B wins when one of the doors 1 and 3 conceals the car. Similarly, strategy A, pick door 1 then switch to door 2, but do not switch to door 3 is dominated by strategy B, pick door 3 then always switch. Dominance is a strong reason to seek for a solution among always switching strategies, under fairly general assumptions on the environment in which the contestant is making decisions. In particular, if the car is hidden by means of some randomization device like tossing symmetric or asymmetric three-sided die, the dominance implies that a strategy maximizing the probability of winning the car will be among three always switching strategies, namely it will be the strategy which initially picks the least likely door then switches no matter which door to switch is offered by the host. Strategic dominance links the Monty Hall problem to the game theory. In the zero-sum game setting of Gill, 2011, discarding the non-switching strategies reduces the game to the following simple variant: the host decides on the door to hide the car, and the contestant chooses two doors. The contestant wins if the car is behind one of the two doors she chose. Solutions by simulation. A simple way to demonstrate that a switching strategy really does win 2 out of 3 times with the standard assumptions is to simulate the game with playing cards. 3 cards from an ordinary deck are used to represent the 3 doors. One special card represents the door with the car and 2 other cards represent the goat doors. The simulation can be repeated several times to simulate multiple rounds of the game. The player picks one of the 3 cards, then, looking at the remaining 2 cards, the host discards a goat card. If the card remaining in the host's hand is the car card, this is recorded as a switching win. If the host is holding a goat card, the round is recorded as staying win. As this experiment is repeated over several rounds, the observed win rate for each strategy is likely to approximate its theoretical win probability. Repeated plays also make it clearer why switching is the better strategy. After the player picks his card, it is already determined whether switching will win the round for the player. If this is not convincing, the simulation can be done with the entire deck. In this variant, the car card goes to the host 51 times out of 52, and stays with the host no matter how many non-car cards are discarded. Confusion and criticism. Sources of confusion. When first presented with the Monty Hall problem, an overwhelming majority of people assume that each door has an equal probability and conclude that switching does not matter. Out of 228 subjects in one study, only 13% chose to switch. In her book The Power of Logical Thinking, Voss Savant quotes cognitive psychologist Massimo Piatelli-Palmerinai as saying, "No other statistical puzzle comes so close to fooling all the people all the time, and that even Nobel physicists systematically give the wrong answer, and that they insist on it, and they are ready to berate in print those who propose the right answer." Pigeons repeatedly exposed to the problem show that they rapidly learn to always switch, unlike humans. Most statements of the problem, notably the one in Parade magazine, do not match the rules of the actual game show, and do not fully specify the host's behavior or that the car's location is randomly selected. Krauss and Wang conjecture that people make the standard assumptions even if they are not explicitly stated. Although these issues are mathematically significant, even when controlling for these factors, nearly all people still think each of the two unopened doors has an equal probability and conclude switching does not matter. This equal probability assumption is a deeply rooted intuition. People strongly tend to think probability is evenly distributed across as many unknowns as are present, whether it is or not. Indeed, if a player believes that sticking and switching are equally successful and therefore equally often decides to switch as to stay, they will win 50% of the time, reinforcing their original belief. Missing the unequal chances of those two doors, and in not considering that /2 gives a chance of 50%, similar to the little green woman example. The problem continues to attract the attention of cognitive psychologists. The typical behavior of the majority, that is, not switching, may be explained by phenomena known in the psychological literature as 1. The endowment effect. People tend to overvalue the winning probability of the already chosen already owned door. 2. The status quo bias. People prefer to stick with the choice of door they have already made. 3. The errors of omission versus errors of commission effect. All else considered equal, people prefer that any errors that they are responsible for to have occurred through omission of taking action rather than through having taken an explicit action that later becomes known to have been erroneous. Experimental evidence confirms that these are plausible explanations which do not depend on probability intuition. Criticism of the simple solutions. As already remarked, most sources in the field of probability, including many introductory probability textbooks, solve the problem by showing the conditional probabilities the car is behind door 1 and door 2 are 1/3 and 2/3 given the contestant initially picks door 1 and the host opens door 3. Various ways to derive and understand this result were given in the previous subsections. Among these sources are several that explicitly criticize the popularly presented simple solutions, saying these solutions are correct but shaky, or do not address the problem posed, or are incomplete, or are unconvincing and misleading, or are false. Some say that these solutions answer a slightly different question. One phrasing is you have to announce before a door has been opened whether you plan to switch. The simple solutions show in various ways that a contestant who is determined to switch will win the car with probability 2/3, and hence that switching is the winning strategy, if the player has to choose in advance between always switching and always staying. However, the probability of winning by always switching is a logically distinct concept from the probability of winning by switching given the player has picked door 1 and the host has opened door 3. As one source says, the distinction between these questions seems to confound many. This fact that these are different can be shown by varying the problem so that these two probabilities have different numeric values. For example, assume the contestant knows that Monty does not pick the second door randomly among all legal alternatives but instead, when given an opportunity to pick between two losing doors, Monty will open the one on the right. In this situation the following two questions have different answers. What is the probability of winning the car by always switching? What is the probability of winning the car given the player has picked door 1 and the host has opened door 3? The answer to the first question is 2/3. As is correctly shown by the simple solutions. But the answer to the second question is now different. The conditional probability the car is behind door 1 or door 2 given the host has opened door 3 is 1/2. This is because Monty's preference for rightmost doors means he opens door 3 if the car is behind door 1 or if the car is behind door 2. For this variation, the two questions yield different answers. However, as long as the initial probability the car is behind each door is 1/3, It is never to the contestant's disadvantage to switch, as the conditional probability of winning by switching is always at least 1/2. 4 university professors published an article in the American Statistician claiming Savant gave the correct advice but the wrong argument. They believed the question asked for the chance of the car behind door 2 given the player's initial pick for door 1 and the open door 3, and they showed this chance was anything between 1/2 and 1 depending on the host's decision process given the choice. Only when the decision is completely randomized is the chance 2/3. In an invited comment and in subsequent letters to the editor, Morganale was supported by some writers, criticized by others. In each case a response by Morganale is published alongside the letter or comment in the American Statistician. In particular, Savant defended herself vigorously. Morganale complained in their response to Savant that Savant still had not actually responded to their own main point. Later in their response to Hogben and Needham they did agree that it was natural to suppose that the host chooses a door to open completely at random, when he does have a choice, and hence that the conditional probability of winning by switching has the same value, 2/3, as the unconditional probability of winning by switching. This equality was already emphasized by Bell, who suggested that Morganale's mathematically involved solution would only appeal to statisticians, whereas the equivalence of the conditional and unconditional solutions in the case of symmetry was intuitively obvious. There is disagreement in the literature regarding whether Savant's formulation of the problem, as presented in Parade magazine, is asking the first or second question, and whether this difference is significant. Beans concludes that one must consider the matter with care to see that both analyses are correct. Which is not to say that they are the same. One analysis for one question, another analysis for the other question. Several discussants of the paper whose contributions were published alongside the original paper, strongly criticized the authors for altering Savant's wording and misinterpreting her intention. One discussant considered it a matter of taste whether or not one explicitly mentions that, which door is opened by the host is independent of whether or not one should want to switch. Among the simple solutions, the combined doors solution comes closest to a conditional solution, as we saw in the discussion of approaches using the concept of odds and Bayes' theorem. It is based on the deeply rooted intuition that revealing information that is already known does not affect probabilities. But knowing the host can open one of the 2 unchosen doors to show a goat does not mean that opening a specific door would not affect the probability that the car is behind the initially chosen door. The point is, though we know in advance that the host will open a door and reveal a goat, we do not know which door he will open. If the host chooses uniformly at random between doors hiding a goat, this probability indeed remains unchanged. But if the host can choose non-randomly between such doors, then the specific door that the host opens reveals additional information. The host can always open a door revealing a goat, and the probability that the car is behind the initially chosen door does not change, but it is not because of the former that the latter is true. Solutions based on the assertion that the host's actions cannot affect the probability that the car is behind the initially chosen appear persuasive, but the assertion is simply untrue unless each of the host's 2 choices are equally likely, if he has a choice. The assertion therefore needs to be justified. Without justification being given, the solution is at best incomplete. The answer can be correct, but the reasoning used to justify it is defective. Some of the confusion in the literature undoubtedly arises because the writers are using different concepts of probability, in particular, Bayesian versus frequentist probability. For the Bayesian, probability represents knowledge. For us and for the player, the car is initially equally likely to be behind each of the 3 doors because we know absolutely nothing about how the organizers of the show decided where to place it. For us and for the player, the host is equally likely to make either choice because we know absolutely nothing about how he makes his choice. These equally likely probability assignments are determined by symmetries in the problem. The same symmetry can be used to argue in advance that specific door numbers are irrelevant, as we saw above. Variance, a common variant of the problem, assumed by several academic authors as the canonical problem, does not make the simplifying assumption that the host must uniformly choose the door to open, but instead that he uses some other strategy. the confusion as to which formalization is authoritative has led to considerable acrimony, particularly because this variant makes proofs more involved without altering the optimality of the always switch strategy for the player. In this variant, the player can have different probabilities of winning depending on the observed choice of the host, but in any case the probability of winning by switching is at least 1/2, while the overall probability of winning by switching is still exactly 2/3. The variants are sometimes presented in succession in textbooks and articles intended to teach the basics of probability theory and game theory. A considerable number of other generalizations have also been studied. Other host behaviors. The version of the Monty Hall problem published in Parade in 1990 did not specifically state that the host would always open another door, or always offer a choice to switch, or even never open the door revealing the car. However, Savant made it clear in her second follow-up column that the intended host's behavior could only be what led to the 2/3 probability she gave as her original answer. Anything else is a different question. Virtually all of my critics understood the intended scenario. I personally read nearly 3,000 letters and found nearly every one insisting simply that because two options remained, the chances were even. Very few raised questions about ambiguity, and the letters actually published in the column were not among those few. The answer follows: if the car is placed randomly behind any door, the host must open a door revealing a goat regardless of the player's initial choice and, if two doors are available, chooses which one to open randomly. The table below shows a variety of other possible host behaviors and the impact on the success of switching. Determining the player's best strategy within a given set of other rules the host must follow is the type of problem studied in game theory. For example, if the host is not required to make the offer to switch, the player may suspect the host is malicious and makes the offers more often if the player has initially selected the car. In general, the answer to this sort of question depends on the specific assumptions made about the host's behavior, and might range from ignore the host completely to toss a coin and switch if it comes up heads. See the last row of the table below. Morgan and Gilman both show a more general solution where the car is randomly placed but the host is not constrained to pick uniformly randomly if the player has initially selected the car, which is how they both interpret the statement of the problem in Parade despite the author's disclaimers. Both changed the wording of the Parade version to emphasize that point when they restated the problem. They consider a scenario where the host chooses between revealing two goats with a preference expressed as a probability Q, having a value between 0 and 1. If the host picks randomly, Q would be 1/2 and switching wins with probability 2/3 regardless of which door the host opens. If the player picks door 1 and the host's preference for door 3 is Q, then the probability the host opens door 3 and the car is behind door 2 is 1/3, while the probability the host opens door 3 and the car is behind door 1 is Q. These are the only cases where the host opens door 3, so the conditional probability of winning by switching given the host opens door 3 is 3 plus Q, which simplifies to 1/1 plus Q. Since Q can vary between 0 and 1, this conditional probability can vary between 1/2 and 1. This means even without constraining the host to pick randomly if the player initially selects the car, the player is never worse off switching. However, neither source suggests the player knows what the value of Q is, so the player cannot attribute a probability other than the 2/3 that Savant assumed was implicit. Endors, D. L. Ferguson, suggests an end-or generalization of the original problem in which the host opens P losing doors and then offers the player the opportunity to switch. In this variant, switching wins with probability /n, now par 1. If the host opens even a single door, the player is better off switching, but, if the host opens only one door, the advantage approaches 0 as n grows large. At the other extreme, if the host opens all but one losing door, the advantage increases as n grows large. Quantum version. A quantum version of the paradox illustrates some points about the relation between classical or non-quantum information and quantum information, as encoded in the states of quantum mechanical systems. The formulation is loosely based on quantum game theory. The three doors are replaced by a quantum system allowing three alternatives. Opening a door and looking behind it is translated as making a particular measurement. The rules can be stated in this language. as once again the choice for the player is to stick with the initial choice, or change to another orthogonal option. The latter strategy turns out to double the chances, just as in the classical case. However, if the show host has not randomized the position of the prize in a fully quantum mechanical way, the player can do even better, and can sometimes even win the prize with certainty. History: the earliest of several probability puzzles related to the Monty Hall problem is Bertrand's box paradox, posed by Joseph Bertrand in 1889 in his Calcul des probabilités copyright S. In this puzzle there are 3 boxes, a box containing 2 gold coins, a box with 2 silver coins, and a box with 1 of each. After choosing a box at random and withdrawing 1 coin at random that happens to be a gold coin, the question is what is the probability that the other coin is gold? As in the Monty Hall problem, the intuitive answer is 1/2, but the probability is actually 2/3. The 3 prisoners problem, published in Martin Gardner's Mathematical Games column in Scientific American in 1959, is equivalent to the Monty Hall problem. This problem involves 3 condemned prisoners, a random one of whom has been secretly chosen to be pardoned. One of the prisoners begs the warden to tell him the name of one of the others to be executed, arguing that this reveals no information about his own fate but increases his chances of being pardoned from 1/3 to 1/2. The warden obliges, flipping a coin to decide which name to provide if the prisoner who is asking is the one being pardoned. The question is whether knowing the warden's answer changes the prisoner's chances of being pardoned. This problem is equivalent to the Monty Hall problem. The prisoner asking the question still has a 1/3 chance of being pardoned, but his unnamed colleague has a 2/3 chance. Steve Selvin posed the Monty Hall problem in a pair of letters to the American Statistician in 1975. The first letter presented the problem in a version close to its presentation in Parade 15 years later. The second appears to be the first use of the term Monty Hall problem. The problem is actually an extrapolation from the game show. Monty Hall did open a wrong door to build excitement, but offered a known lesser prize such as $100 cash rather than a choice to switch doors. As Monty Hall wrote to Selvin, "And if you ever get on my show, the rules hold fast for you no trading boxes after the selection." A version of the problem very similar to the one that appeared 3 years later in Parade was published in 1987 in the puzzle section of the Journal of Economic Perspectives. Nalaboff, as later writers in mathematical economics, sees the problem as a simple and amusing exercise in game theory. Philip Martin's article in a 1989 issue of Bridge Today magazine titled The Monty Hall Trap presented Selvin's problem as an example of what Martin calls the probability trap of treating non-random information as if it were random, and relates this to concepts in the game of bridge. A restated version of Selvin's problem appeared in Marilyn vs. Savant's Ask Marilyn question and answer column of Parade in September 1990. Though vs. Savant gave the correct answer that switching would win 2/3 of the time, she estimates the magazine received 10,000 letters including close to 1,000 signed by PhDs, many on letterheads of mathematics and science departments, declaring that her solution was wrong. Due to the overwhelming response, Parade published an unprecedented 4 columns on the problem. As a result of the publicity, the problem earned the alternative name Marilyn and the Goats. In November 1990, an equally contentious discussion of vs. Savant's article took place in Cecil Adams's column The Straight Dope. Adams initially answered, incorrectly, that the chances for the 2 remaining doors must each be 1 in 2. After a reader wrote in to correct the mathematics of Adams's analysis, Adams agreed that mathematically, he had been wrong, but said that the Parade version left critical constraints unstated, and without those constraints, the chances of winning by switching were not necessarily 2/3. Numerous readers, however, wrote in to claim that Adams had been right the first time, and that the correct chances were 1 in 2. The Parade column and its response received considerable attention in the press, including a front-page story in the New York Times in which Monty Hall himself was interviewed. Hall appeared to understand the problem, giving the reporter a demonstration with car keys and explaining how actual gameplay on Let's Make a Deal differed from the rules of the puzzle. Recent discussion, Over 75 papers have been published about this problem in academic journals and the popular press. Barbeau 2000 contains a survey of the academic literature pertaining to the Monty Hall problem and other closely related problems as of the year 2000, and contains citations to 40 publications on the problem. At present, the book Rosenhaus 2009 has the most recent comprehensive academic survey, and refers to at least 25 publications on the topic which appeared subsequently to Barbeau's book. Since then, another 10 or so publications have come out. A number of sources refer to the Wikipedia article on the Monty Hall problem and the editorial discussion accompanying it, e.g. Rosenhaus 2009, Gill 2010 and several 2011 publications, that in 2012. The problem continues to appear in many venues. Darren Brown explains the Monty Hall problem in his stage show Svengali. After asking a member of the audience to choose the location of his shoe from 3 boxes, he reveals an empty box from one of the ones not chosen. He then asks if they would like to change their mind and recommends that they do so, as it will increase their chances of winning. He explains this further by demonstrating on a large screen the same puzzle but with 100 boxes. The member of the audience decides to stick with their decision and loses. The problem is also addressed in his 2006 book Tricks of the Mind. Penn Jillette explained the Monty Hall problem on the Luck episode of Bob Dylan's Theme Time Radio Hour radio series. Economist M. Keith Chen identified a potential flaw in hundreds of experiments related to cognitive dissonance that use an analysis with issues similar to those involved in the Monty Hall problem. In 2009, a book-length discussion of the problem, its history, methods of solution, and variations, was published by Oxford University Press. The problem is presented, discussed, and tested in the television show Mythbusters on November 23, 2011. This paradox was not only tested to see if there was an advantage to switching versus sticking, but they also tested the behavior of contestants presented with the same situation. All 20 of the common contestants tested chose to stay with their original choice. The problem was also discussed and tested on the television show James May's Man Lab on April 11, 2013. In this presentation, each test was done by presenting 3 identical beer cans, 2 of which had been shaken. James May performed this test 100 times, each time switching his choice from his original choice after one of the shaken cans was removed. In the end, he was doused 40 times, while his colleague Sim, who had to pick the remaining beer can, was doused 60 times. The resulting percentage was roughly what they expected. However, the explanation James May gave was not correct. Craig Whitaker's actual letter to Voss Savant has been found, and his original question reported in Morgan al. Response to Hogbin and Needham: I've worked out 2 different situations. In one situation it is to your advantage to switch, in the other there is no advantage to switch. What do you think? See also, boy or girl paradox, principle of restricted choice, Sleeping Beauty problem, 2 envelopes problem, references. External links: The Game Show Problem, the original question and responses on Marilyn Voss Savant's website, University of California San Diego, Monty Knows version and Monty Does Not Know version, an explanation of the game, Monty Hall at DMOZ, Monty Hall Paradox by Matthew A. McDougall, The Wolfram Demonstrations Project, Monty Hall Problem, Khan Academy, The Monty Hall Problem at the New York Times, The Reserve Player's Chance, a practical example on the Monty Hall Paradox. Stick or Switch? Probability and the Monty Hall Problem, BBC News Magazine, September 11, 2013. Mathematician Marcus Du Soto explains the Monty Hall Paradox. Gatekeeper Game, another web simulation of the Monty Hall Paradox, Science Friday, a Euro sci-fi snapshot, Monty Hall. September 6, 2013. Goldberg, Lisa. Monty Hall Problem. Brady Heron. Retrieved May 27, 2014.